Okay, welcome back to my calculus conundrums. We're going to continue with optimization, and feel free to subscribe if you want to. Okay, we're going to do a little bit business application here. A real estate office handles 50 apartment units. When the rent is set at $5.40 per month, all 50 are occupied. But for each $30 increase in rent, an average of one unit becomes vacant. And then it says each occupied unit requires an average of $36 per month in service and repairs. So what rent should be charged to maximize profit? Okay, so we know we want to maximize profit, but before we can maximize profit, we need to come up with a function that represents the price of the apartment based on the number of units. So what I'm going to do is I'm going to use two values. One value, we know that if 50 units are occupied, that corresponds to a price of $540. Now, we also know that if we increase the price $30, so if we increase it to $570, then only 49 units would be occupied. So basically that gives me 2 points on the graph for the profit function. So I know x is 50, p is 540, and when x is 49, p is 570. So we can get the slope now of this formula. So we can go 570 minus 540 for the numerator, and then 49 minus 50 for the denominator, and we get negative 30. Okay, then we can use the point slope formula, but instead of using y minus y1, I'm doing p minus p1 for price. So now, if we know that x is 50 and p is 540, then what we could do is we could use that point. We can use this point to plug into the equation, and we can solve for the formula for p. So we know that p minus p1, if we're using this point, then that'd be p minus 540 equals the slope times x minus 50. And then if you distribute that, you'll get minus 30x, and there's minus 30x. And then you'll get 1500. And then if you bring this over, that will give you plus 540, and 1500 plus 540 is 2040. So now this gives us a formula for the price. Now, as I said, revenue is simply the number of apartments times the price of each apartment. So if we take this and plug it back in here for price, I probably should have showed you that, but let me just tell you that basically what I'm going to do is plug this in for p, and then you're just going to multiply it by x. So x times minus 30x is minus 30x squared. And then x times 2040 gives you 2040x. So that's the revenue. Now, we know the cost is $36 per apartment because that was given. And now profit, remember, is revenue minus cost. So if I take this, so let me back up again. So if I take this function and subtract this function from it, I'll be taking 2040x minus 36x, so that'll just give me 2004x right there. So my profit function would be minus 30x squared plus 2004x. And now since I want to maximize profit, we'll take the derivative of this, and the derivative of this will be minus 60x plus 2004, and then we set that equal to 0 and solve it. And I know you guys can solve that. Just move your minus 60 to the other side, and then divide both sides by 60, and you get x is approximately 33. So now let's see if we rent 33 apartments, let's see what price that would give us. So minus 30 times 33 plus 2040 gives us a price of $1,050. So the number of rented apartments should be 33, and the price charged should be $1,050 per apartment. And that solves that one. This next problem wants us to find the points that are on this graph, y equals x squared plus 4, that are closest to the point 0, 8. So let me show you the graph. Here's the graph, x squared plus 4, and there's the point 0, 8. Now I'm just going to pick a random point on this graph. Since the graph is x squared plus 4, I can let this point, the x value of this point just be x, and then the y value has to be x squared plus 4. And so what I want is I want to find the distance between this point, and then I want to minimize that function. So we need the distance formula. So we'll take the distance formula and get the distance between this point and this point. So we'll just say x minus 0 quantity squared plus x squared plus 4 minus 8 quantity squared. And of course all that's under the square root for the distance formula. And actually if we square these, it turns out that if you want to minimize a square root, it can be minimized by minimizing the square of the square root. So we can minimize d if we minimize d squared, and that way we can get rid of the square root. So let's square both sides, and if we square both sides, I'll get d squared equals x minus 0 squared plus x squared plus 4 minus 8 quantity squared. And then just use some algebra and simplify this. This is going to be x squared. This is actually going to be x squared minus 4 quantity squared. And then when you square this, you get x to the 4th minus 8x squared plus 16. And then you have another x squared here. So when you put that all together, you get d squared equals x to the 4th minus 7x squared plus 16. And we're just going to say that's f of x instead of d squared. I'm going to call it f of x. So we want to minimize this function. So to minimize this function, I just take the derivative and I get 4x cubed minus 14x. And then I set that derivative equal to 0. So set that equal to 0 and solve it. And I factor a 2x out, and I get 2x times 2x squared minus 7. And then so if I solve for 2x, I'll get x equals 0. But if I solve this equation, 2x squared minus 7 equals 0, I'll get x equals plus or minus the square root of 7 halves. So therefore, I've got maybe 3 options here: 0, minus square root of 7 halves, or plus square root of 7 halves. Now let's apply the second derivative test and see which one of these will minimize that distance. Okay, so let's see if we plug, let's get the second derivative. So the second derivative, take the derivative of this and you get 12x squared minus 14. Now if you plug 0 in, that's going to be negative, so f of 0 is actually a relative max. But if you plug in plus or minus square root of 7 halves, you'll get 7 halves times 12, which would be 84 divided by 2, which would be 42 minus 14, which is positive. So either one of these would make the second derivative positive, and so by the second derivative test, we get a relative min at plus or minus the square root of 7 halves. So the point, the x value, would be plus or minus square root of 7 halves, and then if you plug that back into the formula x squared plus 4, then you'll get that the y value is 15 halves. And so this point that's closest to this point 0, 8 that's on this parabola would be either positive square root of 7 halves and 15 halves, which would be here, or minus square root of 7 halves and 15 halves, which would be right here in this spot here. Okay, so there's actually 2 points that's closest. I'm going to work one more example on this video, and then the last one for optimization will be a trigonometric problem. So don't worry about the last one unless you have to deal with trigonometry, like if you're in a Calculus 1 class. Alright, real quick, a box is to be constructed in such a way that the perimeter of the base is 9 centimeters. Looks like I've got to plug my computer in, so let me pause the video and do. Okay, so where was I? So the perimeter of the base here has to be has to be 9 centimeters, and the perimeter of a side must be 12 centimeters. So find the dimensions that maximize the volume of the box. And so let's take a look at the picture. So here's the base. The base is x by y, and we're going to let z represent the height. Okay, so now we know the primary equation we want to optimize is the volume, and the volume would just be x times y times z. Now, but we know the perimeter of the base has to be 9. So 2x plus 2y has to be 9, which can be simplified to x plus y equals 4.5. And then the perimeter of the xz side, that would be this side, that has to be 12. So 2x plus 2z must equal 12, or x plus z must equal 6. Now, from number 1 here, I can solve this, and I can get y equals 4.5 minus x. And from number 2 here, I can solve this, and I can get z equals 6 minus x. So now I've got y in terms of x, and I've got z in terms of x. So I can go back to my primary equation, x, y, z, and I can say x times 4.5 minus x for y and 6 minus x for z. And then I'll let you multiply this all out. If you multiply all this out, you should get x cubed minus 10.5x squared plus 27x. Okay, so that represents the volume. Okay, so there's the volume. And now we want to take the derivative of this volume so that we can optimize it. So now the derivative of that would be 3x squared minus 21x plus 27. And if I solve this, I can factor out a 3 here, and I get 3 times x squared minus 7x plus 9 equals 0. And so I've got to solve this equation here to get a solution. And this doesn't factor, so I had to use the quadratic formula to solve this. So I used the quadratic formula with a equal 1, b equal negative 7, and c equals 9. And now I'll let you just go through the calculation here, but you know the quadratic formula. So I used the quadratic formula, and I got the answers are 7 plus or minus the square root of 13 over 2, which yields 2 answers, either 5.3 or 1.7. Now I'm going to use the second derivative test, and so I have to take the derivative of this, which is 6x minus 21. You might notice I replaced this. Originally I took the derivative of this, but this isn't the second derivative. This isn't the first derivative. This is the first derivative. So I took the derivative of that, and I got 6x minus 21. Well, now I'm going to evaluate the second derivative at each of these values. So I'm going to evaluate the second derivative at 5.3, and when I plug 5.3 in there, I got a positive number. So 5.3 yields a minimum, and this is the exact value of 5.3. 7 plus square root of 13 over 2 minimizes v. And then 1.7, when I plug 1.7 in there, I got a negative number. So this actually maximizes v. Okay, so that's what I wanted to do. I wanted to maximize v. So that's what I want. This right here. This one's 7 minus square root of 13 over 2, which is approximately 1.7. Now, so there I have my x value, and then just go back into the formulas up here, and you know y is 4.5 minus x. So plug that in, and you get that number. And then z is 6 minus x, so plug x in here to get z, and you get this number. And so the exact dimensions are 7 minus square root of 13 over 2, for y is 2 plus square root of 13 over 2, and z is 5 plus square root of 13 over 2. But if you just want the approximations, it's 1.7 by 2.8 by 4.3. And so that would be the dimensions to maximize the volume of that box. And then I'm going to do one more video, and like I said, it's going to be a trig application.